Hi everyone. All right, let's begin. Okay, thank you for coming. So tonight I'll talk about mutation testing. What is it? How it works? Why you would do that? So I'm Theo Fidry. I live currently in Spain, although I don't speak Spanish at all yet. So you can find me on the social medias. I'm not an English native person, you can tell by my accent. So if at one point you don't understand what I'm saying, don't hesitate to interrupt. I won't take offense. It's fine, don't be shy about it. So a few projects on which I'm working on. Alice, which is a library to help you to generate fixtures for demos or tests. Hamburg and Fiction, mutation testing tools. Coincidence. PHP Scopper and Box, tools to isolate dependencies and build files. I won't dig much into it because it could be a talk on its own. And API Platform, a framework to build APIs, which is, if you ever have to write an API, do check that project first. It's going to help you out a lot. All right, so let's start with a show of hands. No, you need to. Jesus. All right. Who writes unit tests? Nice. Who does TDD? Good. A bit less people, but still good. Continuous integration? Everyone? Yes. Who measures code coverage? Cool. A lot. And who has ever heard or used mutation testing? Quite a few. Nice. All right. So before getting really into what mutation testing is, I'm going to talk a bit more of the problem it's solving and how it's solving it. And for that, we're going to talk about software quality. So according to Marcelo Duarte, who's the creator of PHP Spec, which, if you don't know, it's testing or rather specification tool. So he defines software quality as the extent to which software takes into account what matters most for the customer and the maintainability and the source code. And if you pay attention to that definition, there is you can actually notice two different kinds of quality. The first one is what matters to the customer, which is the external quality, and then maintainability of the source code, which is the internal quality. So if we were to illustrate lack of external quality, so for those who don't recognize, it's a screenshot of Internet Explorer and the Windows XP, so it's a bit old, where you were to accept to install all the tools each software program installers recommended you to install. After a couple of them, you would quickly end up with something like that, which is, well, quite ugly. But if you were to define external quality, could say it's conformity to the user expectations, how reliable it is, the accuracy, ergonomics, design. Another way to define it is the quality perceived by the user. And now if we talk about internal quality, so that's a report from Sensulab Insight, which is a quality analysis tool. So the project for that report has around 20 critical issues, 700 major issues. We can always question if the tool is good at detecting things if it's not false positive, but it doesn't sound too good overall. So a way to define internal quality is maintainability, concision, cohesion, simplicity, clarity of your code, and you could probably add more stuff to that list. But in short, it's the quality perceived by the developer, which is what we're going to focus on right now, because you're developers. So now that we define software quality, there is a question of should we care? I mean, does it have any impact on our products or software? And because if it doesn't matter, really, why should we take any interest into it? So if we look at that graph, you can see it's called project stamina. It's the number of cumulative functions over time. With the red curve, you have so the speed at which you can add new features if you do not care about internal quality. So you can see at the beginning, it's easy because there is nothing, so there's nothing getting in your way. And then, as time passes by, it gets harder and harder. And on the other hand, if you do care about quality, then it's a bit harder at the beginning, there's more stuff to do, but then the rhythm at which you can add new features is more steady and constant. And so the two curves cross a point where it's a payoff line, which is, well, if it was a short-lived project and you stop before that point, well, you're good. It's better off not caring about quality. And past that point, well, it's going to cost you more to not care about it. So you have the sources. We can always debate about the relevance of those graphs, but we can, I mean, intuitively, it makes sense that if you do a small, quick project to get a quick result, if you don't care about quality, it's going to be faster. Whereas as you add more and more stuff, you need to care because otherwise it's going to get in your way, it's not going to work the way you want, and you're going to get slower and slower. So the idea here is that the less you care, the harder it's going to be to add new features. And now if we take a look at bugs, so this graph is the cost of a bug depending on which phase that bug is being discovered at. So you can say $100 during development time on your local machine, whereas on production it's $10,000. So we can always argue about the numbers. You have sources, you have a debate, link to a debate. We can always, I mean, question those numbers. But if we take simple example of a payment system, for example, and you have let's say you were about to ship something to push your code, and then you actually take a bit of extra time to test something and discover a bug, and so you add the test, you fix that bug, you add the test for it before pushing. You took a bit of extra time to fix that bug, to discover it and fix it, so that time is the cost of the bug. Whereas if that bug has been found only during the review process, then, okay, you didn't take that time to find the bug or fix it, but someone else during the review points it out, and then you need to take that time anyway to fix it. So besides your time, there is the time of the person reviewing your code that's being taken. So the cost is increasing. And same idea for QA, it's just you're further down in the process, so it might take time of more people and can take more time to get there. So it's more expensive. And in production, well, that's where we can speculate, but so if we take the example of payment system and say some customers are not being charged properly, and some are being charged twice. Besides the whole process of reporting the bug, fixing it, and we're going through review, QA, and stuff, you also potentially have, you need maybe to pay some customers as, because you screw up. You might have lost some customers as well. You might tarnish your image. It's really hard to quantify, but we can easily see that the cost might just grow exponentially. But now, because we're more talking about code, like we can get rid of the last phase, because after all, even if you test properly, if you review your code properly, there's always the risk of having a test that costs you a fortune. The only difference that you reduce the likelihood of that happening. So if we cut down the last part and focus more on the part we have more control on, and we break down the origin of the cost, so we have the cost of implementation itself. You have the cost of debug and repair, and I mean outside of the implementation phase itself. If you're fixing it locally, it doesn't count. You have the technical debt, which is, if you're not familiar with, the idea is that when you're adding a feature, increase the complexity of systems, so the next feature is going to be a bit harder to introduce, so there's kind of overhead, and that overhead is the technical debt. And then you have the cost of delay. So the cost of delay is the extra you're paying for not fixing the bug earlier. So if we take the bug, the graph before, so if that bug was discovered during the QA phase, so you have that cost, and whereas if you discovered it during the dev phase, it would be cheaper, and that difference of price, of cost, is the cost of delay. So if we were to illustrate that, you start from your idea, you build your feature without caring much about quality, so you have your build cost, and then you have, there's going to be bugs for sure, because you didn't care much about quality, so you have that cost of repair and debugging. Then you get that technical debt, which is, well, the amount of how big the technical debt is depends on how bad the code you wrote is. Whereas if you build the same feature but caring about quality, then the build cost is bigger because you took more time and to find bugs and to write tests. But ideally, you don't have any bugs afterwards, so there's no cost of debug or repair. And the technical debt is lower because you took the time to refactor the code when appropriate, so it's going to be easier to introduce new features afterwards. And so the cost of delay there is that difference. Although it doesn't take into account time, so if your project was so short, I mean, it didn't live long enough, maybe those extra costs did not kick in. So that's why if you build a prototype, for example, you can afford to not care about that because it's not going to live long enough to cost you much with bugs. But the idea is, the more you delay, the more expensive it gets. So why technical debt is an appropriate term, because it's the same idea as debts. If you need to pay interest, and the more you wait, the higher those interest will be. So obviously, the answer is you should care. I mean, no surprise here, but at least we know what the consequences are if you do not care. So now, that brings the question of how you improve that internal quality. And one of the answers, it's not the only one, but the one we're going to focus on tonight, is by adding tests. Now, if adding tests was just a magical solution, I mean, that would be nice, but we tend to forget something with tests, especially when we're not too familiar with tests and we're just like, yeah, tests are a solution, and we add tons of tests. We tend to forget that tests are code, like your source code. It has the same properties. You need to write them. You need to make sure they work. You need to refactor them. You need to maintain them as well. So those are properties of code. So your test, as your source code, is not free. It's, I mean, expensive might not be the right term, but they are not necessarily cheap. You need to be aware that there's going to be a cost by introducing those tests. And the idea is that you need to introduce them only if they're worth it. Besides not being cheap, they introduce their own set of problems. How do you safely refactor your tests? How can you trust a test suite? How can you make sure that your team is writing effective tests? If you're given a piece of code that was not tested, how do you make sure that you added enough tests to safely refactor that piece of code? We can also rephrase it in one question. How do you assess the quality of your test suite? All of that to bring you to that graph. So you have this segment with the cursor, which is your level of quality of your program. That includes your test. On the left-hand side, you have no tests. And on the right-hand side, maximum number of tests, which in practice you can never really achieve, but it's more like something you should go towards. So if you have no test, you have a high velocity on the short term because while there is not that much code to change, it doesn't mean that it's going to be bug-free, but there's just not that much code to change. Whereas if for introducing a small piece of code, you need to change 10 test classes, it's going to take you more time. You're less likely to have a bug, but it's going to take more time, hence a short-term low velocity. And so the idea here is that ideally on your program, on your product, you want to know where you are so that you can know what's left to do to go towards where you want to be. So if, depending on the phase of your development of your product, you need to adjust that. So if you're a startup, you have short deadlines. What's important is getting enough value to get enough fundings to live long enough. Whereas if you're more stabilized product, you have enough fundings, you're profitable. So the idea is you want to bring down the cost of development and of bugs. So you want to be more on max test side. So how do we assess the quality of the test suite? Which, is the idea behind that cursor. That cursor is the answer. How do you calculate, do you know where that cursor is? So a few common answers are, don't worry, it's going to be fine. That's, if you don't care at all, fair enough, at your own risk. I'm a ninja rockstar, I know my tests are good. Maybe a bit of overconfidence, maybe you're a genius, but don't overestimate yourself. I do TDD, so I know my tests are good. That's an interesting point, unfortunately, completely false. Because, well, first, even if you apply TDD, you don't write all the tests, so you have no guarantees that all the code being written has been written following that method. And then there's a question of your test. Do you test drive your changes? Do you test your test? And then what about the testing your tests? And nobody does that. So no, that's not the answer. You then have code review, which actually is a good answer. The problem with it is it's inconsistent and labor intensive. And still hard to get a metric from code reviews as well. And then you got code coverage, which is a popular answer because you get a number and you get that objective number, so people are happy about it. It's like, oh yeah, is our product good? Yeah, we got 100% code coverage. Yeah, perfect. The problem is that it's completely false because the line code coverage doesn't tell you what is tested. We're going to walk through that example to show that. So you have a simple counter class. You have that property count and method count. So we pass a number to that method count. If that number is superior or equal to 10, we increase the counter. Simple enough. We have test for it. One test that makes sure that the counter is incremented if the number passed is above 10. And the other that counter is not incremented if the number is below 10. So with that, we run the tests with code coverage, 100% code coverage, fantastic. So is it good enough? Like on paper, it looks good. I have simple tests, they're easy to read. I have 100% code coverage. But how can we check that it's good enough? An easy answer is by introducing a bug. So we're going to change superior equal to superior. Because we introduce a bug, we expect our test to pick that up. So our test should fail. But if we run those tests, they do not fail. Because our tests still pass, we can say our test suite is deficient. It failed to meet our expectations. And the reason for that is because code coverage is not enough. It doesn't tell you what is tested. If you look at the HTML report of PHPUNit, if you look at the legend, it says executed, not tested. And the tested code is only a small subset of the executed code. What, however, it does tell you is what has not been tested. Because if a piece of code has never been executed, it cannot have been tested. So in our case, we were missing that test case where we make sure that the counter is incremented if we pass 10. If we do add that test, we run the test again, then fine, the tests are failing. So that brings the question of how do you detect that your test suite is deficient? Well, as we just did, by introducing a bug. And that's exactly what mutation testing is about. So the idea of mutation testing is you have your source code. That's cute, rabbit, because your code is beautiful and cute. You got a mutator and go through a mutation process, and then you get your mutant. So if we take the previous example, an example of mutants is changing that superior equal to superior. That's an example of mutant. So you can see other examples of mutators, transforming a plus into minus, superior equal to superior. You are swapping the operator's spaceship. Transforming return true to return false, and there is tons more. It depends of the mutation testing tool you're using, of the language you're using, but I mean, that's the idea. It's very basic transformations like that. So how does mutation testing framework works? So the idea is you have your project with source code, tests, vendors, and others. The testing framework has a file collector, and it's going to collect your source code files. Then it has a list of mutators built in, and those files are going to go through those mutators, and from that, mutants are going to be generated. At that point, a mutant is just the information of changing that piece of code into that, but the code has not been changed yet. We just reached those modifications, but we didn't apply those yet. So, example of mutants with the previous code, well, we have changing number from 10 to 9, superior equal to superior, instead of incrementing the count, we decrement it, and well, there's tons more of mutators, so just a couple of them. So once we have all those mutants, they go for each mutant, they go through building process where we're gonna mutate that code. We're gonna apply the mutants, we're gonna change the code source thanks to the mutator in separate process. Then we're gonna run the test. And from the test we get result if the test passed or not. Because the mutant, in the end, is a bug, you expect your test to pick it up. So what you want is the mutant to be detected, the bug to be detected. So if your test passed, it means your mutant survived, your test failed. If failed as they didn't meet your expectations. If however, the test actual result is failed, then the mutant was killed. It means the bug has been introduced, has been detected, which is what you want. And so from that, you have a set of generated mutants, and for each of those, you know if they have been killed or not. And so from that, you can create that mutation score, which is number of mutants killed by the number of mutants generated. Ideally, what you want is detect all those bugs, so you want all the mutants to be killed. So the result will be 1 or 100 if you want to get percentage, you multiply by 100. So to the original question, how you detect that test suite is deficient, you have two metrics, not one but two. The first one is a code coverage, which is going to tell you what is not tested. The code that's not being executed cannot be tested, so that's the first metric you can use. And the second one is among the executed code, well, you can, the mutation testing score is going to tell you what is definitely tested. So now that brings the question if, does that really work? I mean, you saw the transformations, they are very simple, so does it really detect anything in the end? Well, for those who are curious, there's someone that demonstrated that if you take a complex system, and so there's bound to be complex bugs in it, a way to detect those complex bugs is to try to find out all the smallest bugs you can. And by finding and fixing all those small bugs, you're gonna solve all the complex bugs you can ever find. So it's been demonstrated, so it does work. So it's nice to have that scientific background to back it up. But all right, so this theory is, I mean, it's how mutation testing tools works in general. It's not specific to any language. There's some differences depending on the languages, but mostly that's how they work. That's the idea behind it. But now, let's look at PHP, focus on PHP for a bit. So you have two libraries, Humbug and Infection. Some people are like, yeah, nice, we got choice. And some are like, oh, I don't want to have to find out which one I need to pick. Well, you're lucky in PHP, Humbug has been deprecated for Infection, so you only got Infection. Beta was, it's for beta. All right, so let's begin with demo. So we're gonna use Infection on Symfony dependency injection. Why that library specifically? Well, why not? I mean, it's non-trivial code. It's not like there is tons of code either, but there is sizable size of code. And there is over almost 30 million installs, so it's code used a lot. It's like production code, not just some academic examples. So to install it, because, well, first we clone the project, simple. Because of the weird Symfony management setup, there is no PHPUNIT in that specific component, so you need to install PHPUNIT, and then you can install Infection as well. For those who are curious, the slides will be available online, and it's actual text, so you can copy-paste it if you want to try yourself. So you got the PHPUNIT configuration, simple enough, nothing fancy there. If we execute PHPUNIT, it passes. Okay, that's expected. And then we configure Infection. So for that, Infection has an init command to help you out. It brings an interactive form where it asks questions about how you want to configure it and help you out. And once you did that, you get that infection.json.dist file, where, well, you can see it's relatively simple. Source, that's where you're going to specify the code that's going to be used. You can exclude some of it, like we're excluding the test and the vendor, because that's not what we want to test. PHPUNIT is the entry I had to add manually after the init command, because PHPUNIT is not installed as composer package here, so Infection is not able to pick it up. You need to help it, but that's exceptional. And a log file. So that's a very basic configuration, but that's what you need most of the time, not much more. And then you execute Infection. So you can see there's a lot going on. So let's break it down. Oh yeah, and it took around 15 minutes, whereas the test took 2 minutes before. So
2 seconds.
2 seconds, thank you. So went from 2 seconds to 50 minutes. It's not nothing, but well. So if we look at the beginning, so we are running Infection. You can see we are running Infection with Xdebug enabled. The reason being Infection requires code coverage. So if you don't use Xdebug, you need PHP DBG. But that's also why it's a bit slower, because the tests that took 2 seconds are now taking 26 seconds. And then that's the process I described before. We collected all source code files. It goes through the mutators, which generate those mutants. So you can see it collected around 150 files and generated 3,500 something mutants. And for each mutant, the tests are being executed. And depending on the result, we output something different: killed, escaped, uncovered, fatal, or timeout. They're basically being killed or not. It's just when they're not killed, we tell what happened. So I skip the big middle bit because there's nothing interesting in it. But then in the end, you have that summary where you see the number of mutants and you get the breakdown of how many of them were killed, how many were not covered by a test or covered but they escaped. And what really interests you here is the covered code MSI. That's a mutation score we defined earlier. So 82%, it's a really good number. I didn't check what the code coverage was, but assuming code coverage is good, means it's well tested. And in the configuration, there was an entry for a log file. So if you open the log file, you get something like that. It's plain text, so black and white. It's no fancy color. Maybe you could add something there. But the idea is for each mutant, you get breakdown, like to which file the mutant was applied, what was the mutator. So this here is actually the mutator name. The command used to run the test. You get the diff applied, and you get the actual output of the test. And so if a test escapes, well, you basically can look it up and see the details. A couple of tips, because, I mean, infection is meant to work out of the box like that. You saw it's very simple. Install, init, run it, and done. But it's a bit slow, and you can do a few more things to help it to make it faster. The first one, especially if you're debugging after running it once, okay, you see those mutants were not detected. Okay, what went wrong? And you want to add more tests or debug it. You don't want to run the whole test suite again to find it out. So you can just apply infection to the files that you want to check. And another example is in the CI, you don't necessarily want to run it on the whole project all the time. You can just apply it on the diff of the code that changed in your pull request. So it's a bit ugly, but it's in the docs. You copy paste that, you don't have to remember it, and then you just pass it to a filter, and infection is gonna run only on those files. Another thing is you have that mean covered MSI, so that you have that score at the end, and basically with that you can tell if the score you get is below that number, the command is gonna fail. So that, like for PHPUNit, if your tests don't pass, the result is 1, and if they pass, it's 0. Infection by default is always gonna return 0 unless you specify that option and the score you get is lower than it. To make it faster, you can use threads. We don't do it by default because there's a lot of PHP code that doesn't work with threads, unfortunately. So that's the reason why, but if it does, especially with the unit tests that should work with threads with no problem, you can use that command. If you're on OS X, it's a slightly different one, but the idea is you just take a number of processors. And another option, which is only covered. So earlier in the report, you could see something like not covered, because infection, for legacy reasons, also apply mutants on code that's not covered. It's more like for, I mean, that's how it was before, basically, so they just kept it. But it's a bit useless to some people, at least in my opinion, so there's that new options have been introduced. There's a question of if that option should be the default or not. If you think it is, it should, then raise an issue and, well, we're gonna talk about it. Another feature is profiles. So infection, like other mutation testing tools, has a built-in set of mutators. But you, depending on how strict you want to be with your project or how important that piece of code is, but that other piece is not so important, you maybe want to restrict the number of mutators or add more of them. So with infection, you have something called profile. So add name is the name of profile. So default is the default one, so far no problem. Then you have category of mutators that belong to function signature. So here we disable them. So for example, it's one of the mutators is transforming public to protected. So unless you're working with libraries, that's not necessarily useful to you. And then there's some mutators you don't want to be applied to some part of your code for whatever reason. You can do that easily with, so true value here is name of mutator, and say in your whatever my source, don't mutate the code in my source class create method, or don't mutate any code in that namespace. So with those few tips in mind, we can run the previous command again. So this time we're going to use threads and only mutate the covered code. So on the left-hand side, there was summary before, and on the right-hand side, a new one. So we went from 3,500 mutations to 3,000, and then the time from 14 minutes to 6 minutes. Half the time, roughly. Pretty good. All right, so that's it for the demo. Now, let's go with, let's wrap things up. So when I tested mutation testing for the first time, I was a bit curious of how old it was because I never heard of it. And it turns out we were already talking about mutation testing in the 70s. So it's quite old. And it works fine, it looks fantastic. I mean, to me, it looks fantastic. It tests your test with no effort. So like, why isn't it used at all? Well, it turns out, although it's a great tool, there is a few issues with it. The first one is a maturity problem. If we look at the whole IT scene, as an industry, we're still not testing enough our code. It's getting better. Well, I don't have any numbers to back it up, but I do hope it's getting better. But we are not quite there yet. And if you don't have any tests, mutation testing is not useful for you because it's testing your test. You also have an integration problem. Not every, so here there's a few things to help you out with the CI or debug things more easily locally. Not every mutation testing tool has those, and they've been introduced recently as well. So it's not always as easy to integrate it in your development process. And last but not least, there's technical problem. It's a brute force technique. What does it mean, and why is it a problem? Well, if you have n tests and m mutants, you're gonna run an m test in the end. So if you take Symfony dependency injection, we had about almost 700 tests, which ran in almost 30 seconds with coverage, 1,300 mutants, so that makes over 2 million tests. And in theory, if we were to scale, it would take 53 hours. You can guess, I did not wait 53 hours, and you saw the time, it was shorter. So there is a few optimization strategies. For example, mutating only the covered code, incremental analysis, mutating only the code that has been changed since the last run, parallelism, so that was the threads, equivalent mutants. It's the idea that some mutants are redundant. We're gonna dig into that later. But the idea is if you reduce the number of mutants, it's gonna go faster because there's less mutants. And different level of requirements, it's related to the profile. So it's the idea that you don't necessarily want to be super strict about your product for everywhere. So for example, some parts of your code you want to be super strict about, and some parts you don't care much, so you don't want to be as strict with it. So infection implements a few strategies. So we got to the 6 minutes with them. However, infection is still relatively young. It's a bit older, has a bit over 1 year. So there's still some work to do with it. The first one, which will be very interesting, is supporting more testing frameworks. Right now it supports PHPUNit and PHPSpec, but Behat, Atom, Conception, and others are still work in progress. So it'll be really interesting to support those frameworks as well. The equivalent mutant problem. So right now infection does nothing about it, but so the idea is that some mutants are not useful. So here you can see, sure, changing plus into minus works. It can be a mutant, but it doesn't change actual code behind, so it's not useful. Another example is you have multiple mutants, but you found out that there is 2, 3, 4 of them. Actually, well, 1 or 2 will have been enough. So here, for example, one time we change a sign, one time we change a value, having 1 of them only would be enough. So we estimate that out of all the mutants, about 30 of them are redundant. So if we could get rid of them, well, it would be faster because there would be less mutants in the end. Smart mutators. So depending on the types, there's some mutators that are irrelevant. So here, for example, changing the strict equal to the loose equal doesn't change anything because it's 2 strings, it's strict types, so it's not going to do anything. And right now, infection is not aware of the types at all, so it cannot be smart enough to tell, no, there's no need to mutate that code. Another thing that could be done is more granular configuration. So right now, if you want to be strict about a piece of code but not about another, the best way to go would be either to be able to leverage the mutants in your section, or use different infection configuration files and run it several times with different configuration files. But I think it could be easier to do. Another thing is, so you had that report where you have mutants that escaped, and it's bound to have false positives for whatever reason. Be it legitimate reason, like, yes, there is the type, because of the types it doesn't apply here, or just because it's a piece of code you don't care, or it's a case that you know cannot happen with your system because it doesn't make any sense. And so you can go through the report, see all those false positives, but you can't do anything about it right now. So when you're gonna run it a second time, you're gonna have those same false positives. It would be really convenient if you could just mark them and say, yeah, this one is fine, and when you run it again, you don't get them again. Another problem is IO-bound framework. So the problem is, with infection, when we have a mutant, we are gonna copy your project in temporary directory, apply the mutant there, so change the code in that temporary directory, and then execute the command there, which means it's IO bound. We do that because in PHP we don't have monkey patching, at least yet. If we could somehow have it, we could get rid of that, and it would definitely make it faster. So to wrap things up, the good parts, it gives you feedback on your test. That's the part I think I appreciate the most, because regardless of your level, of your confidence in your test, like be it junior or senior, you have an objective feedback about them. It allows you to test your test with little effort, which is great. It's automatic, there's not much to do. It helps you to discover dead code as, not as code that's never executed, but more as useless tests. For example, you see you have 10 tests, and you find out that if you get rid of 3 of them, well, the code tested is the same. Well, it means those 3 tests were useless, and less code is best. The best code is no code. And so last one helps you to refactor your tests, because yeah, you can change them or get rid of them, add more, and check that your test suite is still as good. So not so good parts, don't say the bad parts, it can be slow. How slow depends on your test, the nature of your test. A handful of young libraries, I'm not talking of just PHP, but in general in the whole IT industry, there's not many major libraries for that. Okay. Writing smart mutants is difficult. It's more technical problem. And side effects with integration tests. What do I mean by that is, well, imagine in your code, there's one functionality which is removing a folder, and you have a test for it, so it tries to remove one directory. And the mutant applied change the directory being deleted, and it would change it to your root system. You're not going to be happy about the result. Well, it's a bit far-fetched example, but more concrete example we had was someone on Linux had a case where when he was running infection, he was running out of memory, so his browser and PHP Storm were getting killed to try to free some memory, which is not super convenient. So we fixed that, but it's like we can't, I mean, it's side effects that depends on your integration test, so the best way to avoid them is to run it in Docker container or just run it on your unit test. My personal experience with it is, well, I'm always a bit upset with it because I need to write more tests, basically. And I would like to just avoid to write, I would like to write less code. But whenever I run it, and I push myself to write a test for it, occasionally I had a case where, wow, what's happening there? And actually it turned out like it was a really nasty bug that took me a long time to debug, but it wouldn't be comparable to the time it would take me to find it if it was reported by someone else, like to investigate the whole thing. Like, it was simplest, I mean, it reports it more easily. And one way or another, you'll always find a bug unless your code is perfect, which is very rare. And last but not least, is very helpful for non-devs. What I mean by that is, if you talk to your manager or whoever your non-technical person responsible of your product, it's always helpful for them to have an objective number than just you saying, yeah, no, it's good, or yeah, no, it's bad. Like having something else, that's a gut feeling, or relying only on the trust of your ability to assess the test, which if you're a junior, might not be the best. If you're a senior, depends on your experience. So you have an objective number, it's a metric, so that's very helpful. So my personal recommendation is use it. It's gonna help you. If you don't, well, at least now you see a kind of method to help you about having feedback about your test and approach your test. If you're more interested in mutation testing, I have that repository, Awesome Mutation Testing, where I listed all the mutation testing tools in other languages as well, and there is some papers regarding mutation testing. So you can check it out. All right, so we're a bit over time, but so you can find, I'll publish my slides on LinkedIn. Please leave some feedback on it. I would really appreciate it. And I guess that's it. It's time for questions.
I have two questions, actually. The first question is the result the same on every run, or is there a sort of random element in it?
No, the run is deterministic. So you have those mutators, they're always going to produce the same result. Unless you have mutators that introduce a random thing, but we don't have those. So you're going to, if you run it 2 times consecutively, you're going to get the same result.
And the second question is, you already talked about that when integrating mutation testing in your CI workflow, kind of to set the minimum expected MSI score. Yeah. And the problem I always face is, how do I find that reasonable number?
Well, that was about the cursor graph that earlier that I showed before. That score tells you where you are, and the score, and then it's up to you to know where you want to be, and your ability to assess what's left to do there. So it really depends on your projects, your ability, and skills of your team. Like you need to take the decision. It's same for coverage. Like it's you who decide, do I want to have 30% of code coverage, or 70%, or 90%? It's your decision, and depends on the context of your situation, basically.
Hi, thank you for your talk, really appreciate it. I've been using Infection for quite some time now, and what I really find mind-boggling is sometimes I need to do testing on Boolean flags, as they are called, and with the mutator flipping true to false and false to true is a little bit against the expectation I'm setting in my unit test. Do you have like a good advice on how to actually wrap this mutation in such a way that my unit tests are going to pass even after the mutations?
It's a good question. Tricky. I'm not sure. I think the work to be done here is the profiles as which mutators are going to be applied. So we can create more profiles, like be more strict or not. And then, I mean, have the false positive tracking, like, because basically what you want is just mark, yeah, no, that's good, and don't apply it again. But yeah, that's still open issues, unfortunately. I would really like us to tackle that problem, but it's not trivial to do.
Hey, great talk. I appreciate it.
Thank you.
Yeah, you showed us some numbers. Let's say I give it 53 hours to run all the mutations, and it says, well, you got 1 million mutators that have gone through. Is there a way to see a hotspot? Where do the infection come from? So I need to go into the code to see where I have to start. How to find the biggest hotspot?
Well, to find what is being applied and where, you'll need to wait for the report right now. Yeah. So at least right now, there is not dry run mode. So you always need to run the test. But it would be interesting to have it where you just generate the mutants and the report tells you, and so that you have those details, but without waiting for the result. Okay. So that's something missing. If you're interested into it, open issue and we can look into it.
Okay, great.
Hello. Do you have a plan to generate unit tests that will cover found test? Your mutations that you found, to generate tests that will cover that?
At least personally, I don't have that plan yet, but...
You do now.
I'm not alone in that project. Yeah, I don't know. You can try to open an issue and see if there is people interested in it, and they are. It's something that we can try to achieve. So there's always a question of how we'll do that, but open issue and we'll see.
More questions? Okay, thanks. Thanks for the talk.
Thank you.